Okay. Hello, Richard Venditti here again. Today we're going to have a lecture in our advanced recycling course on the repulping or the pulping of recovered paper. And what we're going to do is we're going to have a broad overview of the different mechanisms that occur in pulping. We're going to look at the different types of pulpers and the advantages and disadvantages of each. It's mostly an introduction level at this point, getting you to know the technology. Okay, the first thing we're going to cover is the pulping of recovered paper, just a definition, okay? And the definition is a device whose objective is to convert waste paper into a slurry of well-separated fibers and other waste paper components. That's the definition. If you have something like that, it's considered a pulper. Okay. Now, the important thing about a pulper is it's the first step in our process. So the first step is probably the most critical step in paper recycling. Okay? Now, if we do not pulp properly, in other words, if we don't separate the fibers and separate the contaminants, none of our downstream operations are going to be effective. So that's a key thing to pulping. The second thing is that if we incorrectly pulp, let's say we over pulp, a very bad thing can happen. We can actually destroy our fibers. We can actually cut the fibers, generate fines, and for that reason, we're going to have an inferior pulp material for paper making. Okay, now pulping, the main function is to disperse the recovered paper into separated fibers in the water. That's the main function. But if a pulper only does that, there's going to be some problems. We use the pulper for many different objectives, and I list them here on this slide. So in many cases, what we try to do is if we're going to do de-inking or removal of adhesives or plastics from the surface of the fibers, we need to impart mechanical forces so that we can detach the contaminants from the fibers. If contaminants are left on the fibers or fibers are left on the contaminants, the removal of the contaminants is near impossible. The second objective that a pulper can do is mix the paper with water and chemicals. So in some pulpers we will bleach. For instance, for newsprint you might add some peroxide to a pulper. And so the pulper has a lot of shear action, good mixing. Okay, another objective of pulping is to maintain the contaminants as large as possible. Okay, the larger contaminant is, like we talked about in the lecture last time, the easier it is to remove because it has different size or properties relative to the fibers. Okay. The fourth objective is to avoid damage to the fibers. As we said, we can really destroy the pulp quality if we over pulp the material and cut fibers, generate fines. The fifth item is removal of large debris from the system. Many pulpers are equipped with some type of large debris removal equipment so that we don't plug up pipes and pumps and downstream operations. So that's removal of large debris is a very important part of pulping. Okay, when we talk about pulping, we can break it down into some categories so that it's easier to think about and understand all of the pulpers. The first kind of comparison we can make is batch pulping versus continuous pulping. In batch pulping, the feed, recovered paper, the chemicals in the water are all charged at the beginning. The pulper pulps the material, and at the end of the pulping process, the product is removed. And this process is repeated time and time again throughout the day. Now, the other way you can do pulping is continuous pulping. In this case, the feed, recovered paper, water, and chemicals are continuously fed to the pulper. And the pulper is always in motion, agitating and pulping. And at the same time, there's always an outlet of the pulped material. Now, for a continuous pulper to work, you must be able to distinguish between the unpulped material in the pulper and the pulped material in the pulper. In other words, usually continuous pulpers have some type of screen at the bottom. When a fiber has been liberated from the other fibers and contaminants, it will pass through those holes in the screen and leave. Unpulped material will remain in the pulper until the mechanical action or shear action breaks it down and it can go through the holes. So continuous pulpers have to have some type of mechanism to only allow pulped material or mainly pulped material to leave the vessel. Okay, now another thing that we can talk about is pulping consistency, and there's two categories, low and high consistency. Just as a reminder, consistency is defined, and when we talk about consistency, the solids weight of a sample divided by the solids weight plus the liquid weight. And the solids weight can include fiber and non-fibrous material like clay or coating. And that's we usually call percent K, as it's expressed as a percent if we multiply by 100%. And low consistency is usually at 3 to 6% consistency, and high consistency can be 8 to 20% consistency actually. Now the important thing to think about in these two types of pulpers, or one of them, is the processing difficulty with high consistency pulping. Low consistency pulping at, let's say, 5% consistency, the pulp can be poured out of a jar, so it's pourable. It's relatively easy to pump. Now with high consistency pulping, the pulp is more like oatmeal or very, very thick material. You can just imagine if you took pulp and squeezed it with your hands moderately, you could make a clump of pulp. It would have a lot of water in it. It might be around 15–20% consistency. If you put it on the table, it would not flow. Now that causes us some problems. So when we agitate this material, that's okay. When the impeller is keeping everything in motion, that's fine. But when we need to finally pump it out of our system, we do have some issues that we have to deal with, and we'll talk about those in a little while. Now, I'm just going to briefly go over the general parts of a pulper. This is a generic pulper, and let's just kind of talk about some of the things that we definitely need to have in order for a pulper to work. The first thing is, number one, we need to have a feed method for our recovered paper. So usually it's a conveyor, it's an inclined conveyor, and it's fed by, it usually has some kind of, at the inlet entrance is at a warehouse, and operators will break open bales and push the bales onto this conveyor, or they'll put actual bales onto the conveyor, and there'll be wire cutting processes to cut the wires. So the conveyor conveys the recovered paper into the pulper. Second thing we notice here is all pulpers are usually some kind of container, like a tub. Actually, there is a case, a continuous drum pulper isn't really a tub, but for most pulpers we've got some tub, which is just a walls. It's got to be mechanically strong to hold the hydraulic and mechanical forces that occur in the tub. Third thing we have is the rotor. The rotor actually imparts the mechanical energy to the pulp, and that's what starts off the process of defiberizing. Typically it's a rotating disc with teeth for low consistency, and a helical spiral for high consistency pulpers, and we'll look at those later. And then fourth, we need to have, in most cases, in almost all cases, baffles. Baffles are going to resist the swirling, which is inefficient motion for pulping, and it's going to redirect the pulp towards the rotor. The fifth thing that we'll see is the dilution water feed. So we've got to have a way to get our dilution water into our pulper, and also we need to have a place to add chemicals, not shown on here. The sixth item is the pulper exit. And the pulper exit looks pretty simple, but actually pulper exits can be pretty complicated. As I said before, in many cases we need to have some kind of barrier screen here so that unpulped material remains in the pulper and pulped material can proceed on in the process. Okay. Now, the next thing I want to just talk to you about is just general forces that occur in the pulper. And these different forces have different effects on the paper and fibers. So it's important that we kind of go over the different forces. Mechanical forces are the first force that you'll come across. And these are caused when that fast-moving rotor, that spinning rotor, actually impacts the paper that we're trying to break up. And those mechanical forces will defiberize. So, and obviously, faster rotor speeds cause more intense mechanical forces in the pulper. And these can, depending on your conditions, if overdone, damage fibers. But very effective in low consistency pulping to defiberize. The second pulper force are hydraulic forces. And hydraulic forces actually occur because of the motion of the rotor. The motion of the rotor actually moves the fluid. And then the fluid moving causes hydraulic actions or viscous actions on the paper to be repulped. For instance, if we take a look here at this pulper, we're looking at the top view here, and this right here is the rotor. It's moving in this direction, and we have some baffles to redirect some of the flow. For example, if we look at point A right here, what we'll notice is that the rotor is moving fluid in the counterclockwise direction on the bottom part of A, and the baffle actually, this baffle right here, is redirecting some flow in the, it's going to turn and go in the clockwise direction. So you see you have fluid going in this direction and fluid going the opposite direction. So at point A we have this viscous effect where there's two flows opposing each other, and if there are unpulped material in there, those mechanical actions the opposing flows will use viscous forces to break up the fiber bundles or actually detach ink, which is a great thing. Okay, the last force in a pulper is what's called attrition. And attrition is, has been used in typically only in continuous not in low consistency pulping. Attrition, what it is the mechanical shearing forces that occur between the rotor. For instance, here's my side view. Here's a rotor. It's moving this way. And the bottom of the pulper, okay? And that's typically an extraction plate with holes in it. So here's a side view. Here's the rotor moving in this direction, and here's the bottom of the pulper, which is stationary. Here's a top view where the rotor is moving this way, and the bottom of the pulper, stationary with the holes in it, is right here. Now what happens is that big flocks of material, fiber bundles, get trapped between the rotor and the bottom of the pulper, and what happens is that causes an intense cutting action, and that can cut fiber bundles, it can cut contaminants, but it's a pretty intense action. Overdoing attrition can really hurt fibers. What happens is these fiber bundles are broken up, the fibers are broken up, and when they are of appropriate size to fit through those holes, they will go through the holes. And that is, so you can see that for high consistency, what would happen would be that high consistency pulp would remain in between the rotor and the bottom of the pulp, and it would just get, it would plug the holes, and you would you'd have to cease operations. So attrition is something used in low consistency pulpering. It can be somewhat damaging to fibers, but it's a pretty intense action that breaks up fiber bundles and other contaminants. Okay. So those are the three main types of forces in a pulper. They included mechanical action, rotor right onto the paper fibers. It included hydraulic forces, liquid, and that liquid can contain fibers, and then attrition. Now I'm just going to generally go over some, describe low consistency pulping and high consistency pulping for you. Okay, low consistency pulping, as I said before, around 3 to 6%. The rotor is typically at the bottom of the pulper. It can actually be on the side of the pulper in some cases, but mostly in the bottom. And it usually has a low profile with some teeth that are sticking up, and it's rotating at high speeds. The rotating rotor causes a vortex, and that can cause spinning, which is inefficient use of our mechanical energy, and so baffles are typically in place in different places. Here we're showing some baffles down here low, and those baffles are to disturb the spinning motion of the fluid. Low consistency pulping with the high mechanical forces due to the impacts of the rotor can damage fibers and break contaminants. So there is an issue with low consistency pulping of breaking fibers, and what needs to occur. Typically, low consistency pulping is used for tough fibers, and I'll say this right now, tough fibers being unbleached OCC. Okay, now we can compare that low consistency pulper to this type of pulper, which is a high consistency pulper. All right, the consistency here is generally 8 to 18%, and the first thing that you notice is that the rotor in the pulper is not low profile, it's a higher profile. It's a helical screw. And what occurs is that we need this high profile rotor, because what happens is that rotor spins around and it actually grabs pulp from the top and brings it down to the bottom. And so we need this big rotor with a lot of motion, a lot of moving area to take the pulp from the top and bring it down to the bottom. If we look back at the pulper diagram, what occurs in the pulper is that the pulp here actually comes down to the rotor, it's pulled down, and it actually moves in a circular pattern. And it makes, like, if you look at it from the top, it looks like a donut. And that pulp will go and circulate this way. There will also be motion if you're looking down clockwise or counterclockwise, depending on your helice. But there's going to be this downward circular motion, and it'll look like a donut here. Okay? So the high-profile rotor is very important. The other thing that we'll talk about with high-consistency pulping is that at the high consistency, there is a lot of fiber-fiber rubbing. Okay? At low consistency, there's a lot of water. There's not a lot of fiber-fiber rubbing. But in high consistency, these fibers are in such a concentration that there's a lot of rubbing. And also, the viscosity of the fluid is much higher. So the increase in fiber concentration and the viscosity increase of the material, these will combine to increase the rubbing action. And that rubbing action is a nice gentle action that can detach inks and toners and contaminants, and it can also defiberize, so separate fiber bundles. So we've got a nicer, gentler rubbing action with high consistency. That's useful for fibers that are pretty sensitive, weak fibers that might be kind of wimpy and break if we had mechanical actions, intense mechanical actions applied to them. Okay, so to compare low versus high consistency pulping, I've generated this table. Okay, so the first thing we'll notice is this is low consistency and this is high consistency. Consistencies, again, around 5% for low, around 15% for high. The rotor divided by the tank volume, first thing we'll notice, for low consistency, it's about 0.1%. So that means that 0.1% of the tank volume is occupied by the rotor, very small amount. For the high consistency pulper, because the material will not flow by itself, and because the material is so viscous, we need to have a much larger rotor that can grab pulp from the different areas of the pulper and agitate it. So what you notice is that the high consistency pulper has 8% of its volume taken up by the rotor. Now the specific power, that's the power to run the pulper, is 6 kilowatts for low consistency, and it's 22 kilowatts for high consistency. It's much higher because the higher pulper has to do more work to move the higher viscosity material, to agitate the higher viscosity material. Now you might say, oh, well that's not very good. It seems like the high consistency pulper is of lower energy efficiency. However, if you look at the specific power consumption, I'll skip down to the bottom here. Now the specific power consumption is actually the kilowatt hours. So, actually the specific power was power, it wasn't work, excuse me. The specific power consumption is going to be Now we've got units of kilowatts hour, so it's work or energy consumed per ton of paper. Now, if you notice here, low consistency, it's 30 to 45 kilowatt hours per ton. And for high consistency, it's 15 to 25 kilowatt hours per ton. So what's going on there? What's happening is, even though it takes more power to run the high consistency pulper, you have much, much more fiber in the pulper at one given time. So if you divide things by the tons of paper that you're pulping, it actually turns out that it takes less energy or work for the high consistency pulper to pulp a ton of pulp of recovered paper than it does the low consistency. So that's an important point, that actually the high consistency pulpers on a per ton recovered paper pulped basis are more energy efficient. The rotor speed also I'll mention 16 to 21 meters per second, so that must be a tip speed of the rotor, versus 8 to 15 for the high consistency pulper. So what that says is that the rotor in the high consistency pulper is moving a little bit slower. And it can move a little bit slower because the high consistency pulper is depending on the rotor tip impacting the fibers and the paper and breaking it up. So the rotor tip has to move very fast. So it's got to hit, that rotor tip has to hit that fiber really, the paper really fast to break it. In comparison, the high consistency pulper is actually, it's just gently moving that pulp around, and actually where the rubbing and the breaking is occurring is when the pulp is rubbing against each other. So it can go more slow. Okay, so this just kind of reviews what I said. Rotor speed is slower for high consistency pulper, causing less damage to fibers via mechanical forces of the rotor. That's important if we have wimpy fibers that are going to break in a pulper. Attrition forces are not used for high consistency pulping. Obviously that high consistency pulper would, those holes in the screen would plug. And so for high consistency pulping, without the attrition forces, there's less fiber cutting and contaminant breakage. Okay, so the results of those two things are that when you pulp with high consistency pulping, you should get higher tensile strength, burst and tear strength, than if you pulped from low consistency. So it just shows you that high consistency pulping will cause less damage, give you better properties of your pulp afterwards. Okay, now the other thing that high consistency pulping does is, because there's more fiber to fiber rubbing, that action actually detaches contaminants very well. So the detachment of ink from fibers is especially important when we're going to go do de-inking. So high consistency pulping is often used prior to de-inking. Okay, so just kind of as a review, printing and writing grades that consist of high content of fully bleached hardwood and softwood fibers that are wimpy, they're susceptible to damage. We're going to use gentle high consistency pulping is preferred. Okay, those printing and writing grades are usually going into ink removal operations, and again, high consistency pulping with lots of fiber rubbing is preferred. Now, in contrast, OCC recycling. Now you have, it's a historically older technology, and low consistency pulping is a older technology. Typically it's done at low consistency, partly because of historic reasons, but another reason is that low consistency pulping is a rapid way of pulping, and the unbleached OCC fibers are less susceptible to damage, so they can still make quality pulp with the attrition and mechanical forces that up here. Okay, so that basically kind of is an overview of the differences between low consistency and high consistency pulping. Now I'm going to just kind of show you some, or talk to you about screening and junk removal in a pulper. One of the sub-objectives that I mentioned was to remove large debris. Okay, this can be wood. It can be wet strength paper that's unpulpable. It can be plastics, films, and large pieces. It can be baling wire, nails and bolts, all these kinds of things. container packing materials such as styrofoam, all these things can be in there. And the removal of debris helps protect downstream equipment. You don't want glass and metals to scrape your centrifugal cleaners, for instance, that are probably made out of plastic. And it also prevents plugging of downstream equipment. Okay. Now, when we talk about debris removal methods, we have to go back to our categories because the debris removal methods depend on the type of pulper. Okay. So we have the high consistency batch pulping, and they typically have either two methods, high consistency pulping with a dilution zone or high consistency pulping with a detrasher. And we'll talk about both of those. And low consistency pulping, typically you can have a pulper that has a ragger and junk tower, and other continuous low consistency pulpers have a detrashing system, and we'll look at both of those also. Okay, first let's go to the high consistency batch pulper with a dilution zone. Okay, so here we have our pulper, and this has been hand drawn by me, and I don't claim to be an artist, but that's our helical rotor right there. And what we do is when we fill up this pulper, we're going to fill it up to this pulping level right here. Okay, so we'll fill it up with water and recovered paper, and we'll do our pulping. Okay. Now, at the end of the pulping process, we're going to add dilution water to the system. We'll add dilution water up to some dilution level here, and we're going to get the consistency down to 5 to 6%. Why do we do that? Because at that consistency, we can pump the pulp out of the pulper. Okay, so what happens at the end of the pulping process? Well, okay, first we dilute with water, so now we're at 5 to 6% consistency. Now in the bottom of the pulper we have an extraction plate. So it's a plate with holes in it. And at that lower consistency, the pulped material and some of the small unpulped material will go out the exit port, and that exit port will be a little bit bigger. This is not to scale. And then it would go through a valve. So we're opening this valve at the end of the pulper, and here's our accepted stock. Now this extraction plate with the holes is going to block the large debris. That will remain in the bottom of the pulper. And when we're done extracting all of the pulp that we can, and the level's gone down, now we're just left with large debris here. This valve will close. This valve right here will open, and the large rejects will be discharged out this valve here. Okay. So that's the way that's one of the ways to remove debris in a high consistency batch pulper, called with a dilution zone. Okay, the second way that we can do it is to use an external detrasher. Okay, so basically here the pulper is full when we're pulping at high consistency. So there's just one pulping fill line right here, and here's our helical rotor. And what will happen is we'll pulp, and at the end of the pulping process, we've got this material again at, let's say, 18% consistency. It won't flow, it will plug things up. So at the end of the pulping process, what we'll do is we'll open up this valve and we'll add dilution water to the bottom of the pulper. So we're not diluting all of this material, but we're just diluting the bottom material here. And what that will do, and we'll open up this valve, our exit valve. And so the dilution here will dilute the material to about 5 to 6%. We'll dilute a little bit more. Well, actually, the combination of that dilution water and that dilution water will get us to about 5% consistency. And so we've got this 5% consistency pulp coming out the exit here, and we'll just continue to do that until we empty out the entire pulper. Now at the same time, that pulp is going to an external detrashing unit. That's what this unit is right here. This is not drawn to scale, so actually this detrasher is going to actually be much smaller. It probably is like a 10th or a 20th, I'm not exactly sure, the volume of the pulper. So the pulper should be much larger, but I'm expanding this portion just so that we can see the parts of the external detrasher. The external detrasher is just it's a cylinder here. It's got a screening plate here at the end. And it's got a spinning rotor here. It's a little mini pulper, actually. It's a little mini continuous pulper. I never really actually thought of it like that myself, but when that pulp is coming in, some pulp is actually leaving through this screening plate. So the rotor actually agitates all the material. The pulp comes in at 5% consistency, it goes through these openings in the screening plate, and it goes out the accept outlet. The large debris, things like sneakers and plastic bags and mannequins and CDs, they won't be able to fit through these holes. They'll fall down to the bottom of the detrasher. Okay, and so when all of the pulp has been removed from the pulper and has gone through the detrasher, then what happens is that this valve is closed, water is filled up in here, and then this large debris is pushed out this valve, this reject outlet, which is opened so that we can clean this out. Then this valve is closed again. The pulping process the pulper is filled up again, pulped again, and then again we're going to repeat the cycle. Okay, those were the two types of high consistency debris removal methods that we can talk about. And now I want to talk about continuous low consistency pulping. This is a very common pulper that we see here. It's going to have a ragger and a junk tower. So this is continuous. So what's not shown here is that there's usually a conveyor. It's usually dumping in continuously bales of I'll call it liner board because this is very commonly used for liner board as an example. Now, something interesting about this is that the bales that are coming into this pulper, they have the wires on them. The wires remain on the bales. They're cut. So the wires are cut, but we leave the wires right on the bales, so they're loose on the bales. And there's a special reason why we do that. The bales of recovered paper come into the pulper. Water also comes into the pulper. We maintain it at a low consistency. We've got a low profile rotor down here. It's spinning and it's causing mechanical action to break up our recovered paper. Our accepts actually go through the bottom of the pulper. There's an extraction plate with holes, and the accepts come down here and are taken forward in the process. Now, the rejects can be removed either from the junker or from the ragger, and we'll talk about both of those. The ragger is actually, it's actually a very interesting thing. It's a snake of plastics and wires that is pulled out of the pulper. So what happens is we usually dip a rope into the pulper, and what happens is the swirling wires and plastics wrap around that around that rope. And this ragger has a pulley system, and that pulley, pulley wheels pull this rope out of the pulper. And what happens is the rope, this snake, never ends. It's a never-ending snake. If we continually put in wires and plastics into this pulper, then this snake continues to grow. And if we match the growth of this snake with some velocity of removing the rope, then we get a nice, stable, continuous de-ragging process. So it's kind of a unique process, very interesting, and it works. It removes the wires and large plastics. Now, the other thing that can occur here is that the heavy materials, the large materials, are actually thrown to the outside of the rotor. They're not pulped, and they go into heavy rejects fall down here into a junker tower, and the light large debris is thrown this way and floats up here, and the light rejects are in the top of this tower. It's a water-filled tower, and this claw comes down and intermittently scoops out the light and the heavy rejects. And that's another way to get rid of some of the large debris in a continuous low consistency pulper. So, like I said before, these types of pulpers are often used for an OCC recycling process. And the next couple of slides that I have is just going to show you some actual photos of an OCC recycle mill in which we're showing you the operations around the pulper. Okay, this right here actually just is the warehouse where we store our recovered OCC bales. You can see that I might, if a person is standing up, I might come up to about this height right here, so I'm probably the height of 1 quarter bale. And so you can see that this is probably, I don't know, 30, 40 feet high stack of bales of OCC. It's a pretty dangerous place. These bales, if not stacked and stored properly, they can fall over, and there's always a huge flammability issue in a warehouse like this. So we have a lot of OCC stored. If you think about it, OCC recycle mills are going to process about, they can process in the order of 1,000 tons per day. So you need 1,000 tons of material per day stored just for your production. Okay, now those bales are taken by a front loader. So an operator has to take those bales with a little forklift truck here, and we're showing them pushing them on the storage floor, and they're going to probably pushed onto some type of pulp, onto a conveyor, a paper conveyor, not a pulp conveyor. Okay, now these are the bales that are on the conveyor. They're going up the conveyor and into the pulper. Now the first step that occurs, at least in this mill, is that there's an automatic wire bale cutter. So you can see right here, this is a wire cutter. It's just a long, strong blade. It comes down intermittently every foot or so, and it cuts the wires. It's kind of hard to see here, but there are wires strapping the bale tightly. So it's going to cut those wires, and then the wires and the bales are going to go up the conveyor into the pulper. And like I said, we intentionally leave the wires on because it helps the ragger operate. Okay, so here are the bales cut after cutting, going up the conveyor to the pulper. Okay, so here's our pulper. This might be 15 or 20 feet tall. And it might be about 30, I'm estimating here, 6, 12, could be about 25 feet high in diameter, 25, 30 feet in diameter. And here you see a bale, and it's falling down into the pulper. The rotor is down here. Okay? Now here's the ragger. It actually is this thing right here. And you can see here's the swirling pulp from our pulper. And then the ragger is actually pulling this snake, and you can see that it's got wires and plastics and all kinds of stuff that we can't make into recycled paper. So this snake is actually being pulled out of the pulper in a continuous manner. Okay, and this shows you again that ragger. Here's the wheel, one of the wheels actually right here, and these wheels are moving in such a manner to move this snake out at a certain velocity so that it gives it enough time for enough wire to wrap on so it's strong enough to be pulled out. A very efficient and clever way to remove contaminants from a pulper. The same pulper has a junker claw, and here's the junker claw. It might be 4 to 6 feet wide, I'm estimating. And that junker claw again is going to go down, dip down into this tower, which collects all the large debris thrown from this rotor, and the large debris is just taken out by the junker. Okay, so that is one very common way in an OCC mill to remove contaminants from large debris from a continuous pulper. Now, another way that a continuous pulper can work is the following. It has what's called an external detraction unit or process. And we've got to kind of pay close attention to what's going on here. What we have here is we've got our pulper. Our pulper is right here, and it's being fed continuously. And so that pulper is being fed continuously. Heavy rejects actually are falling down to the bottom of the pulper, and we've got two valves here. This valve is usually in the open position, and the large contaminants fall down, and this valve is closed. When you get a large enough amount of contaminants here, that valve will close, that valve will open, and will intermittently dump heavy rejects. So that's one part of this pulper. The other part of the pulper is that some of the pulp stock, or the stock, let's call it, actually flows over this weir, and then it comes down through this pipe right here, and now what we have is basically a external detrasher, somewhat like what we had for the external detrasher for the high consistency pulper. So basically here we've got a rotor, and the rotor is backed by a screen plate right here, and the pulped material goes through that screen plate and it's exited out, and I'm sorry but part of this has been cut off, but here's the acceps of that screen, and so here's the acceps of our pulping process. Okay, now the unpulped material, things like large flocks and material like that, they're small enough to be pulped. So what we do is we take those and we push them. They are pushed up to this drum detrashing unit. Now the drum detrashing unit is a spinning cylinder. It's got these baffles here to direct the material down this way, and it's got a perforated cylinder. So somewhat pulped material will go through the perforations in the cylinder. They'll go through this pipe and they'll be sent back to our pulper. Because if you think about it, that material was too big to go through these screens, the openings in these screens, but was small enough to go through these openings in this drum right here. So they'll go back into the pulper, they'll get pulped up a little bit more, and then maybe the next time they'll go through this screen. Now what happens here is that the material that can't fit through those perforations continue down through the drum. They are rejected out the end of the drum, and these are our light rejects. So we get two streams. Heavy rejects and light rejects are our rejects, and we get our accepts out this part right here. So that's another common continuous low consistency pulping process. Now, as always, we've got the exception to our rule. We've got those nice classifications, and now what we're going to do is we're going to throw in a different type of pulper. It's a drum pulper, and it's a pretty unique, kind of clever type of pulping process. It's actually a continuous, high consistency pulping method. Now, again, I told you that we weren't really going to use continuous methods for high consistency pulping because we have to have some extraction plates, and those will get plugged up if we have high consistency pulping. Now, the way that this drum pulper works is that we're going to have a high consistency zone and a low consistency zone, and the low consistency zone will be where we do our screening. Okay? Now, the drum pulper is basically, it's very much like a lime kiln in looks. It's an incline rotating drum. It rotates at 11 to 17 RPMs as a general range. The paper is put in one end, and the drum is very large. It's approximately 10 feet high and 100 feet long. Okay, now this schematic, and I wish it was a little bigger, but this schematic kind of shows what's going on. This is the end view of the pulper, and what happens is the paper is put into the drum pulper, which rotates, and the pulper is moving this way. These baffles in the end of the drum pulper pick up the paper and the water, and pick it up and then drop it, and continue to pick up and drop, pick up and drop, pick up and drop, pick up and drop. And this is a nice gentle pulping action, picking up and dropping. It's actually so gentle that it's mainly drum pulpers are used for newsprint, which is easy to pulp. Remember that newsprint or mechanical pulps have low strength, and those low strength pulps actually can be broken up pretty easily. So we use drum pulping as a method to pulp up low strength types of paper. Now, okay, so we have two zones in this drum pulper. We've got a high consistency zone and we've got a low consistency screening zone. So the paper comes in, the paper is lifted and dropped, lifted and dropped, lifted and dropped. That is the pulping process, and that's at high consistency. Then we come to a screening zone. In the screening zone, what we're going to do is we're going to add water to get down to a lower consistency. And then this screening zone right here, this cylindrical part of the drum is going to have openings in which the pulp material can go through. So the pulp material will go through these openings, and that will be our accept pulp. Coming out the end of the drum pulper will be all our rejects that were not pulped. And these will be And I say it kind of sounds funny, but this reject stream is a beautiful stream. There's basically no fibers in there, and all the reject material, things like soda container cartons and things like that, plastic bottles, metals and plastics, they're usually very large and undamaged. So what's happened is we haven't broken down this debris into small pieces that could actually go with the pulp. We've left it as large. And so we get a very beautiful reject stream, as funny as it sounds. Okay, I've got some video to show you on this. This is the beginning of the pulper, the drum pulper, and here are the teeth, the gears, and actually there'll be a motor that will move the drum pulper with these gears, and you'll see this drum rotate. So let me start that up. Okay, so here are those gears moving, and then here's the drum pulper, and you can see how it's massive, and it's rotating, and that rotation is lifting the paper up, it's dropping, lifting it up, dropping, lifting it up, dropping, lifting it up, dropping, and this ends the high consistency zone of that drum pulper. Okay, and now this is the low consistency screening end of the drum pulper, and it's very hard to see here, but that also is going to be rotating to serve the purpose of screening. So let me just go back now. Now I have to go back. Okay, so here we are again.
Just advance to the next slide.
Okay. Whoa. Just let this run. Okay, let me see how this works. So we're having a little AV difficulty, but that's okay. We'll get through this. So that's an overview of that pulper. Now, the next thing I want to show you for that pulper is the rejects outlet. It's really interesting. I made a kind of fool of myself saying that it's beautiful, but it is beautiful. If we take a look here, okay, let me just come back. Can we stop the tape, Bill? Is that possible?
You're rolling.
Okay, we're back. I think this is going to give you a really good picture of why the drum pulper is kind of unique, and how I was saying how beautiful the rejects are. This is the end of that rotating screened area. You can see the baffles that are actually causing the material to not short circuit the entire screening process. And you can see the debris falling out the bottom of that spiraled screening operation. You notice that there's really, you can't see any fibers. It's a very, very efficient way to separate the reject debris from the pulped material. It's really, I would consider it a beautiful method to separate debris from recycling. Now what I'm going to do is I'm going to try and get my laptop back up. Okay. And then the next slide here is just going to give you an overview with some cutouts.
One more time. One more F8. Okay.
Okay, this next picture is going to give us a nice cutout overview of the pulper. The paper feed comes in right here. It's dropped down. You can see here these yellow things are baffles that are picking and lifting the paper up and dropping, dropping, and dropping. Then we've got our low consistency zone. We've got our spray where our water is, where we're decreasing the consistency. The good material comes out the bottom, out through the screen, and then the rejects is exited out this back and are thrown away. We can talk about some of the advantages. Very gentle pulping, keeps the contaminants large and minimizes fiber degradation. It's a simple operation that includes screening, so we get a lot of good screening out of this. Some disadvantages: it's high capital cost, it's got a very large footprint, and it's not an aggressive pulping method. So, for instance, if we had wet strength papers in OCC and we want to try to pulp them, this would not be a very good option for pulping that wet strength material. But you will see some drum pulpers. I've seen several in the United States with newsprint de-inking mills, and they seem to work well. And I've also heard reports of using them for mixed office waste somewhere in West Virginia. Okay, now I want to just kind of summarize. There are several methods to do pulping. We talked about low and high consistency, batch and continuous. The way of choosing which one, sometimes you have no choice. It's historical that pulper has been in your mill. Other cases, these pulpers have been placed in position in a process such that they're going to perform best with the fiber and contaminant that they're supposed to deal with. The main objective of pulping is to defiberize. Everyone knows that. However, secondary objectives are very important also. We've got to remove large debris. We've got to detach contaminants if necessary, like in de-inking, or even in OCC, detaching tapes and plastics and adhesives. We do not want to destroy the fibers, obviously. And we want to mix, in some cases, we want to mix water, chemicals, and fibers. Final thought, and I mentioned it before, if pulping is not done properly, then subsequent processing steps will be ineffective, and the product quality of the pulp will be unacceptable. So if we don't pulp properly, screening, cleaning, flotation, washing, none of those will work. And if we overpulp and break our fibers, then I don't care how clean the fibers are, those fibers will go on a machine, they'll make inferior strength or optical or surface properties, or drainage or runnability on the paper machine, and those will not be useful also. So we've got to be very careful. Our final thought is we've got to do pulping. It's the first step, and it's the most critical step in our recycling. And that will end our lecture for today. We did a broad overview of pulping, and in the next lecture, we're going to talk a little bit. We're going to start to talk more about debris contaminants, like these high-density cleaners. That will be the next step in our process. Thank you.